Welcome back, Marauders. This video, 16.6, we'll be talking about weak acids. So in our last video, we talked about strong acids, and we said that strong acids are ones that ionize completely, so they give away all of their hydrogen ions when they form a solution. The difference between a strong acid and a weak acid is that weak acids do not dissociate completely. So this is a general equation for any kind of acid. HA just stands for any kind of acid. We know that acids always have hydrogen in their formula because they need to be able to donate a proton. And then A is just whatever the anion is that's along with that hydrogen. So this is a generic equation that could work with any acid. So the acid donates its hydrogen to water, making hydronium, and then what's left is A-, which is your conjugate base. So we have an acid, HA, and then your conjugate base, A- after it's lost the proton. So the difference between a weak acid and a strong acid is that this reaction doesn't go to completion. In a strong acid, 100% of the acid donates its proton to water, and so at the end you have all hydronium and conjugate base, and you have none of the acid left. With a weak acid, some of it dissociates and some of it gives away its hydrogen ion, but a lot of it stays as the acid at the end. So we have a two-sided arrow here to show that it's a weak acid, and an equilibrium is going to be established where you have some product being produced, but you have a lot of the reactant still left at the end. So we'll write an equilibrium expression. So for our equilibrium expression, on the top we'll have hydronium, H3O+, and the other product is A-, the conjugate base. And then on the bottom, you'll have your reactant, the acid, and then water doesn't need to be included because it's a liquid. So this is your equilibrium expression, just like from the last chapter. And the equilibrium constant will tell us how much of it becomes product and how much of it remains as a reactant. So this is showing the difference between a strong acid and a weak acid. For a strong acid, Ka is large. Remember, Ka large means that it favors the products, and very little reactant is left at the end. We usually, for a strong acid, just ignore equilibrium and say that the reaction just goes one way, and however much of the acid you start with, 100% of it turns into hydrogen ions and the conjugate base. So for calculating the pH of a strong acid, it's usually pretty easy because the hydronium concentration is just equal to whatever the initial concentration of the acid was. Weak acids are a little bit different. Ka is small, meaning that it doesn't only make products, but a lot of reactant is left over as well. So we have a lot of reactant left at the end and just a little bit of product made. We have the arrows going both ways to show that an equilibrium is established. And the hydrogen concentration is going to be much, much less than the original concentration of the acid. Here's kind of what they would look like if you could zoom in and see all the molecules and ions. So for the strong acid, none of it is present as the acid. It's all present as conjugate base and hydrogen or hydronium ions. And then with the weak acid, most of it is present as the acid. So most of these are staying together and didn't donate their protons. And just a small fraction of it has become hydrogen ions and the conjugate base. So here, basically 100% of them ionize. Here, only a small fraction of them ionize. So Ka is going to tell us how strong or weak an acid is. It's the acid dissociation constant, Ka. And if Ka is a big number, it means it favors the products. So that would be a strong acid. Most of it becomes hydronium ion. And if Ka is small, then it's a weak acid, and most of it remains as the reactant, which is just the acid. So in this question, we're going to try to find Ka. So it gives us some information here. A 0.85 molar solution of phenol acetic acid, which is HC8H7O2, has a pH of 2.68. Calculate the Ka of this acid. So it's an equilibrium problem. We'll write out an equation for an acid, HA, plus H2O makes, so it's an acid that donates its hydrogen. A- will be our conjugate base that's left, and then H3O+. So I didn't write out the whole formula for this acid. I just saved some time and space and just wrote A, which is just the generic formula for any kind of acid. I could have also written it out like this without the water. So water ends up just being kind of like a spectator. If we write it this way, you get the conjugate base and hydrogen ions. So remember, hydronium and hydrogen can be used sort of interchangeably. Since this is an equilibrium problem, I'm going to make an ice table. So I'm going to have my initial concentration, the change in concentration, and then the concentration at equilibrium. So I'll draw columns for each of the reactants and products. If you wrote out your equation with water, you could just cross that one out because water is a liquid. Its concentration doesn't change and it doesn't show up in equilibrium expressions. So our ice table will just look like that. Then we can write an equilibrium expression. So Ka is going to be products, so conjugate base A minus, and hydronium H3O plus. And then on the reactant side we have HA. And like we said, water does not need to be included because it's a liquid and its concentration doesn't change. Okay, so it tells us that the initial concentration of the acid is 0.085, so that's going to go here. 0.085 is your initial concentration of the acid. The conjugate base and hydronium ions are going to start at 0 before this reaction starts to take place. And then it tells us what other information. It tells us that the pH is 2.68. So we're going to need to use the pH to find the hydronium concentration. So pH is just another way of expressing the hydronium concentration. And so we know that the H3O plus concentration is going to be 10 to the negative pH. We know the pH, so we know that H3O plus is equal to 10 to the negative 2.68, which is 0.0021. So I found the hydronium concentration based on the pH. So that's going to be your equilibrium concentration of hydronium, so 0.0021 molar. And so now I can figure out the changes. If it started at 0 and goes up to 0.0021, then we know it changed by 0.0021. This conjugate base is changing at the same rate because it's a 1-to-1 ratio, so it's also up by 0.0021. And over here, your acid had to decrease by that amount, 0.0021, because it's on the other side of the equation. So as these are being produced, this has to be reduced or used. So we can subtract here and find the equilibrium concentration of the acid. It's gone down a little bit. It's 0.0829 is your concentration there. All right, so now that I have the concentrations at equilibrium, I can plug those into my equilibrium expression. So on the top, I'll have my conjugate base, which is 0.0021. I have the hydronium, 0.0021. And then on the bottom, I'll have my acid, 0.0829. And then I can calculate the equilibrium constant, Ka, which is 5.31 times 10 to the negative 5. So that's the value of Ka. That tells me how strong or how weak this acid is. If it's a really, really small number, it means that not very much of the products are produced, so it means it's a weak acid. And as the number gets a little bit bigger, the acid becomes a little bit stronger. We make a little bit more conjugate base and hydronium as Ka gets higher and higher.